So let's start. Thank you very much for the organizers for giving me the opportunity to talk about this subject. Okay, so as advertised, I will talk about bimetric and multimetric theories of gravity. So I will describe what they are, etc. So this, of course, this work is completely, totally classical. So I was about hesitant. I was a bit hesitant to talk in a quantum gravity series. So I thought, okay, finally, it's not quantum gravity, but it can be part of all of that, basically. So, okay, so let's start. Yeah. So in this work, this is a list of my collaborators. So currently, it's Joachim Flinkman and Mikita Kotik. And then I have my earlier collaborators here, the list. And then I have a very important disclaimer that this is a subject on which many people have worked. Here, however, in 1 hour, I will not be able to talk about the subject in general. So I will mostly concentrate on my own work with these collaborators. And as a result, of course, I will be missing lots of citations to other people's important contributions, for which I apologize beforehand. So that's a shortcoming. So yeah, so with those apologies and caveats, I will start now. Okay, so what kind of theories do we consider in this talk? So first of all, we all know about general relativity. So I start very basic. So again, apologies for those who already know about the subject. So we start from general relativity, and we know that this is a theory of a gravitational matrix G mu nu, which is a field of spin 2 and mass equal to 0. So that is basically general relativity. Now, in this theory, we consider extensions of general relativity, which are called bimetric and multimetric theories. These are basically theories of gravity, which is described by a matrix G mu nu, coupled or interacting with a number of other spin 2 fields, which we can call like F1 mu nu, F2 mu nu, etc. So basically, we are looking at a theory of gravity, but instead of one spin 2 field, we have a number of spin 2 fields, so 2 or more than 2 spin 2 fields. And we would like to consider these kind of theories. So what is the physical content of the theories? First of all, the spectrum of the theories. These theories will always contain, first of all, a massless spin 2 state, which is like the analog of the massless graviton or massless gravitational waves. And then we will have a number of massive spin 2 states. So in a theory with 3 spin 2 fields, one of them will be massive and two will be one of them will be massless and two will be massive. So this is the very general structure. We will always have one massless spin 2 field and all the remaining ones will be massive. And this is basically related to the fact that we have only one copy of general covariance in space-time. Okay, so those are the generalities basically. So we are looking at theories of spin 2 fields as stated, and I told you what the spectrum is. Okay, so now we have some important questions that I will try to kind of answer in this talk. So why are these theories interesting, first of all? Secondly, what are the challenges? What are the difficulties in constructing and studying these theories? And finally, what is the progress so far? So where we are in studying these theories. So what is the motivation, the interest, what are the challenges, and what is the progress so far? So I would like to kind of at least shed some light on these three questions during the course of this talk. Okay, so first we start from the basics. And before we start, I just want to remind you about the notion of ghost instabilities in field theories. So a ghost basically is a field with negative kinetic energy. That's something standard that we know. So for example, you have a Lagrangian, which basically is it consists of kinetic energy minus potential energy. And the kinetic energy term basically starts from velocity of the field squared. That's a very standard structure. And this is a healthy theory. But if your Lagrangian contains the velocity of field squared, which is a kinetic term with a minus sign, then that's a ghostly theory, and this field phi would be a ghost. So that's a general notion of a ghost in field theory. These are fields with negative kinetic energy. So what is the consequence of having a ghost in the theory? So first of all, at the classical level, we generically have classical instabilities in the sense that unlimited energy can be transferred from the ghost field to other fields in the theory in the presence of interaction. So the ghost field can acquire more and more negative kinetic energy, and by energy conservation, the extra energy can be transferred to other fields. So you end up with a kind of infinite source of energy for other fields, which of course is not what we see. Such theories would be unstable. And if you quantize these theories, then you will end up with negative probabilities and violation of unitarity in the quantum theory, which is again unacceptable. So basically, we don't want to have theories with ghosts. Okay, of course, there's a big dispute about this, whether these theories can be made reasonable or not. But in general, we start from this point of view that in general, we do not want to have ghosts in field theories. And this is a very, very strong and important constraint on field theories. Okay. So now that we have looked at the notion of ghosts, let's look at their importance in the structure of field theories and in constraining the structure of field theories. Okay. So we know that if we have a field or a particle of spin S, see if S is the spin of the field, then the total number of degrees of freedom can be 2S plus 1 maximum. So you have a spin S, and then you can have helicities from minus S to plus S. So in total, 2S plus 1 states. And this is the case if the mass of your state is non-zero. If the mass of the state is 0, then generically you have two helicities, like two helicities of a photon, two helicities of the gravitational wave, or you have just one component for a scalar field. For example, for a real scalar field, you just have one component. So for massless fields, the number of degrees of freedom, by which I mean propagating degrees of freedom, are maximum 2, depending on their spin. And for massive fields, they are 2s plus 1. So that's the number of degrees of freedom that you want to have for a field of spin S. Now, in reality, what happens is that because of Lorentz invariance or general covariance, whenever you write a field to describe a state of spin S, which is greater than 1, you actually need many more degrees of freedom than the 2s plus 1 that correspond to various helicities. So examples are well known. So if you want to have a field of spin 1, which is like the photon, you will have 2 degrees of freedom for a massless field, or 3 degrees of freedom for a massive field. That's 2s plus 1. However, we know that to describe this, you need a field A mu, which has 4 components. So the number of components in the field is more than the number of states and the number of degrees of freedom that you want to have at the end of the day. And when you go to spin 2, then you describe a spin 2 field by a metric G mu nu, which is symmetric, and it has 10 components. However, for a massless spin 2 field, you know that the number of degrees of freedom must be just 2, and for a massive one, it's 5. So helicity is plus 2, 1, 0, minus 1, and minus 2. Okay, so again, you can see that the number of components in the field, the number of components is much more than the number of degrees of freedom that you want to describe finally. And as you can see, as you go to higher and higher spins, you need more and more components in the field. Okay, and these are redundant components that you do not actually want. So somehow you have to get rid of them. The theory has to get rid of them. Okay, now these extra components generically always contain ghost fields. So these unphysical components always contain at least one ghost mode, which you of course want to eliminate from the theory. And generically, these ghost modes are eliminated by symmetries or constraints, or a combination of symmetries and constraints. And the question is, for a generic theory, do you have enough symmetries and constraints to eliminate the ghosts or not? And the answer is no. If you just write a theory for a higher spin field, you do not have enough constraints and symmetries to eliminate these ghosts. Okay? An important example of this is a theory for a massive spin 2 field where you want 5 degrees of freedom. However, a generic theory will contain 6 degrees of freedom, so you do not have enough constraints to remove this extra degree of freedom, and this is a ghost. So this is the well-known Boulevard-Dazer ghost from 1972, basically. Okay. So now the absence of ghosts, demanding the absence of ghosts, is a very, very powerful tool in defining a field theory, especially when you combine it with Lorentz or general Lorentz invariance or general covariance. So when you combine these two, these conditions are basically enough to determine the basic structure of your field equations. The examples are very well known. So for spin 0 field, you have the Klein-Gordon equation. For spin half, you have the Dirac equation. Spin half, you have the Maxwell-Yang-Mills equations. Spin 2, you have the Einstein equations. These and if you go beyond that, actually, even string theory, the most of the structure of string theory is essentially determined by the requirement of absence of ghosts and Lorentz invariance, basically. Okay, so these conditions are very, very powerful, and our basic equations that we use in field theory are essentially determined at the basic level by these requirements. Okay, so now you can see that there's a dichotomy. Okay, so first of all, these equations at the basic level are given by the requirement of absence of ghosts and general covariance or Lorentz invariance. But then you can notice a dichotomy here. First of all, so when we look at standard model and general relativity, we see that in the standard model, you have, of course, fields of spin 0, spin half, and spin 1 that appear, but you need them in multiplets. So you have a kind of intricate structure of these fields, various combinations of them appearing with some structure, and that is what gives you finally a physical theory which describes nature. But when you look at general relativity, it's a theory of a spin 2 field which is massless, and in fact it's the simplest possible theory that you can write down for a spin 2 field. So there's a dichotomy. If you want to describe particle physics, you need spins 0 to 1, but the structure is complicated. It's not the basic equation that can do the job. You need to do more work to get the correct theory. But for general relativity, it's the basic equation that's in the most simple form that gives you the physics. Okay, so that looks like a dichotomy. So then clearly you can ask the question, okay, what happens if you go beyond GR? What happens if you want to also construct more complicated theories of spin 2 fields? Okay, so now we can look at this from a slightly different angle, which is that we look at classifying our various theories based on the spin content of the fields. So if we look at fields of spin less than 2, then these theories are well known. Okay? And these are the fields that basically enter the structure of the standard model: spin 0, spin half, spin 1. We know them. We even have spin 3 half, which is not in the standard model, but we know the theory for that field, which arises, of course, in supersymmetry. Then you can look at theories with spin greater than 2, and then you see that there's a big qualitative difference between them, that once you go to spin greater than 2, then the understanding is that there are no local theories with finite field content that could describe them. You basically need infinite tower of fields. You need spin 3, spin 4, spin 5, the infinite tower. You cannot just truncate the tower. Okay? And of course, these are higher spin theories and string theory. So you see that there's a big difference between if you want to stay below spin 2 or if you want to go above spin 2, then the nature of the theories change completely. Okay, so then the question is, what about spin 2? So if you now look at the boundary, which is spin 2, then there we know that general relativity is the simplest possible theory that you could write down. And this we now see from this point of view is exactly equivalent to the equivalent of massless Klein-Gordon theory for spin 0 and Maxwell theory for spin 1. Okay, this is the simplest possible theory that you can write down for a spin 2 field, which is ghost-free and generally covariant. So it's just at the same level of Klein-Gordon theory and Maxwell theory. So that's again the dichotomy that we see. By contrast, if you look at a standard model of particle physics, then you have all kind of the scalar field comes as a Higgs doublet. Then you have the gauge multiplet structure, etc., and that you need all of that to give you a physical theory. So again, you see the dichotomy here. But now the dichotomy is even more pronounced because now you can see that this is a very this dichotomy appears just at the boundary of spin 2, because if you go above spin 2, then you have a completely different kind of structure. You have to go for non-local theories and things like string theory and higher spins and all that. So you cannot have local field theories with finite field content. So we are just at the boundary of these two types of theories at spin 2. And the only theory that we know very well is GR. But this dichotomy with the standard model tells us that, okay, maybe what if you need more than GR? Can you actually construct something more complicated or not? Okay, so then the question is, do theories of multiple spin 2 fields, theories that have a structure more close to the structure of the standard model, do they actually exist or not? Or is GR unique? So this is just a mathematical question. Is GR is general relativity the only consistent theory of spin 2 fields? Or you can actually construct more complicated theories of spin 2 fields? So that's the kind of question that one can ask. And this is the kind of question that we would like to address here. So we are basically exploring this kind of unexplored corner in the space of field theories, which is a corner consisting of interacting spin 2 fields beyond the single massless spin 2 field of general relativity. So that basically is the motivation for this kind of studies. So just to recap, why are we interested in theories of multiple spin 2 fields? So this is an uncharted corner of the space of local field theories, which is difficult to probe. Furthermore, it has interesting features. So first of all, being spin 2 theories, they are of course closely related to gravity, which is a spin 2 theory. The content of these theories essentially could constitute dark matter. You have a number of spin 2 fields which are weakly coupled to gravity and to other matter fields, as we will see. So they are good candidates for dark matter. And as you will see in these theories, you naturally get properties that essentially are equivalent to cosmological constant or dynamical version of the cosmological constant. So you have good dark energy candidates in them. Of course, you can study inflation in these theories. It has interesting features. Okay. However, of course, none of this is required. Like we don't have any evidence that we have to look at higher spin theories or massive spin 2 theory, multiple spin 2 theories. So then basically our approach is that, okay, these theories are not demanded by experiment, but they are motivated by experience, because from experience, we know that whenever people constructed consistent field theories, it turned out that they had relevance for nature. So that itself is a good motivation for studying these theories and figuring out, okay, do these theories really exist or not? So this is essentially the final frontier that we have in the space of classical field theories, which we have not explored. And by this, I mean classical field theories with finite field content, which by definition means that we have to restrict ourselves to spin 2 and below. So that's the motivation part. And now we will start looking at the examples of these theories and what the challenges are, basically. So historically, for spin 2 theory, this is a very kind of short historical timeline. Of course, GR we knew in between 2015-17, around that time, Einstein came up with GR. So then Fierce-Pauli introduced a mass for a spin 2 field at the linear level. Van Dam, Veltman, and Zakharov, they discovered the discontinuity that if you take the mass of a graviton to 0, then you do not really recover massless gravity. Einstein came up with this notion of the nonlinear effects, which essentially kind of removed the VDVZ discontinuity. Bulwer and Dazer essentially taught us that theories of massive gravity generically have a ghost. So theories of spin 2 fields beyond general relativity generically have a ghost. And Isham Salam and Stratdi introduced theories of dynamical spin 2 fields, like two dynamical spin 2 fields interacting with each other. They, of course, were not ghost-free, but they studied them. And then these are more recent papers that essentially led to the development of the kind of theories that we will consider today. Okay.
So can I ask a question?
Yes, please.
Just thinking about the theoretical motivation.
Yeah.
Stellar gravity, of course, it has ghost. There is tensor ghost.
Yeah.
But it has a property of renormalizability. So,
Yes.
and is it possible to having multimetric theories to achieve renormalizability?
In principle, so if you're asking if one could generalize multimetric theories to stellar kind of theory, yes, you can do that. Yes. So
And
then essentially, sorry.
And also achieve renormalizability in some way.
I have not looked at that, but that's probably likely possible. So that basically means that you combine these theories with scalar fields in some way.
Okay.
Basically, yeah. But I have not actually looked at that. That's a very good question, but I have not looked at that. Yes.
Excuse me, Philippe also would like to ask
yes,
questions.
Yes,
Philippe,
yes, please. Philippe, please.
Yes, good morning. I think you're interested in more than one spin 2 field, provided the equations of motion are still second order.
Yes,
rather
exactly.
Than what Shravan was mentioning, what I've been looking at is
exactly. So yes. Yeah. So right now, this is what we are looking at. But of course, in principle, you could go beyond second order and see what happens. But you are perfectly right that right now, at the basic level, we are looking at second order. Yes. Thank you.
Okay, then I'll just ask one more question, if I may.
Yes.
What is the problem with the FG theories that Salam was working on?
They have ghosts.
So you have some way to handle that problem. So
exactly.
Basically, your talk is a way to handle the FG ghost problem.
Exactly. So the main part of the talk is to exactly look at that theory, their theory, and come up with a formulation which is ghost-free. And then the second part of the talk, we will go beyond two fields. So we will look at a multi-spin 2 version of that. I think that's a very good way of summarizing it, basically. Yes. Thank you. Okay. So now we start from basics. So we want to write down a theory of general relativity plus one spin 2 field. And we want to look at a generic such theory. And we will start from the kind of formulation where we have a spin 2 field, which we call the matrix. That's the supposedly gravitational matrix. And we have another spin 2 field, which we call F mu nu. And this is our extra spin 2 field that we want to couple to gravity. So we start from a Lagrangian, which first of all has an Einstein-Hilbert term for G mu nu. That's our gravity theory. And we want to write an interaction. Now, when writing the interaction, I impose an extra condition or requirement that the interactions are non-derivative. I do not want to put derivative terms in interaction. In general, of course, you can do that, but the general analysis and general features of those theories are not yet known to us, so we don't know about them. At least I don't know about them in general.
Excuse me. Yeah. Excuse me. And are you supposed to put some kinetical restriction on phi itself? Not in the interaction term, but on phi F field itself. What
on F?
What is the form? Yes. Yeah, what is the form of kinetic term?
I will come to that. That's a very good question,
okay,
very important question.
Sorry.
I will come to that exactly.
Sorry.
Yes, yeah. So yes. First of all, let's look at just the interaction without bothering about the kinetic term for F, which of course should be there. Now, if you look at this theory where F does not have a kinetic term, this is generically called massive gravity. So what is F here? F is now a God-given field. You have to give me some F mu nu. You can call it eta mu nu or some F mu nu, and then this theory will be a theory of massive gravity. Okay, so yeah, so that's a massive gravity, and historically F mu nu was taken to be eta mu nu, and you take this potential in such a way that when you linearize the theory, you produce the Fierce-Pauli mass for the matrix. That's massive gravity. But if you look at how many degrees of freedom this theory propagate, you would like it to propagate 5 degrees of freedom because they have a massive spin 2 field. So you want helicities from +2 to -2. But in reality, this theory always propagates 6 degrees of freedom for a generic potential V. Okay, and the 6th degree of freedom is a ghost. So this is a helicity 0 state, and it's a ghost basically. Okay, so that's the problem. This is what is called a Boulevardizer ghost in general. Okay. Okay, so this is the problem with these kind of theories, and this
Sorry, Fawad.
Yes.
Is this Lagrange you are showing as a first example invariant under diffeomorphism?
No.
No, right? Because
No.
you have a flat metric.
Exactly, because you have a flat metric. Of course, you can, even if you put some general F mu nu, the point is that this F mu nu is not dynamical.
Mm-hmm.
So somebody must give you this F mu nu, and once you are given that F mu nu, then you have a fixed metric. You can introduce general covariance by introducing extra Stuckelberg fields and all that, but in reality, you don't have general covariance here. Okay. So this is not a general covariant theory, exactly. So this is one of the kind of shortcomings of this theory. Mm-hmm. It requires a God-given F mu nu metric, and it's not general. It doesn't have general covariance.
Okay, I see, thanks.
Yeah, but still ignoring those issues, just to solve the ghost problem, a lot of work was done on this theory. So then there are these papers, and in particular, the paper by Cremonelli, Nicolis, Papucci, and Trenchini. They introduced a formalism which proved very influential for developing this theory. And then, of course, the papers by Deram Gavadadze and Tolly that were very crucial for discovering the ghost-free version of this theory. And then our later works on this that I will describe now, basically. Okay, so yeah, okay. So now we have this theory, but of course, as was pointed out here, we need a kinetic term also for F mu nu. So what is that? So let's just add a kinetic term here, okay? And that, of course, makes F mu nu also dynamical. So we have now two dynamical spin 2 fields interacting with each other. But of course, we have not specified these interactions and these dynamics. So then the questions that arise are, what is this interaction potential between the two spin 2 fields? So what is F? What is the potential V? And what is the kinetic Lagrangian for F? So we need both of these quantities. We need to know them. And once we have a proposal for these two functions, that's we have our theory, then of course we have to go back and carry out the analysis and show that this really is a theory of two interacting spin 2 fields without a ghost. Okay, so we need to then do the we should be able to do the ghost analysis and show that there is no ghost indeed in this theory. Okay, so I will kind of briefly go through this stuff. So first, let me first describe the nature of this interaction term. So this is the most crucial part of this theory. So what is this? Okay, so this can be actually understood very nicely in terms of well-known quantities. So this is a complicated looking structure, but it can be understood very easily. So to understand that, first we go back to something very, very old, and that is the notion of elementary symmetric polynomials of a matrix S. So suppose we have a matrix S, which is a 4x4 matrix for us. So we take a 4x4 matrix S, and it has eigenvalues lambda1 to lambda4.
Excuse me, you suppose that metric is Hermitian?
So this S is not Hermitian, no.
Not Hermitian, okay, no. Thank you.
So this S is any real matrix. So I take it to be real, but it's not even symmetric. So it's not Hermitian, it's not symmetric, it's a real matrix, but it's a general matrix. So it has 4 eigenvalues, lambda1 to lambda4, but because it's not symmetric, you cannot necessarily diagonalize it. You can write it in some Jordan block form, but you cannot diagonalize it. But in any case, given this matrix S, you can define its elementary symmetric polynomials. There are 4 of them. The sum of eigenvalues, which is the trace of the matrix, is the first elementary symmetric polynomial. The product of 2 eigenvalues, all summed up, is the second elementary symmetric polynomial. The product of 3 eigenvalues summed up is the third elementary symmetric polynomial, and the product of all eigenvalues is the fourth one, and clearly the fourth one is the determinant of the matrix S. All the higher elementary symmetric polynomials for this S are 0. Okay, and this is for a 4x4 matrix. If you go to higher matrices, 10x10 or 15x15 matrices, then there the higher elementary symmetric polynomials also will be non-zero. Okay, so this is very simple. This was of course known to Newton, or maybe at least to Newton. So we have the elementary symmetric polynomials in terms of eigenvalues. Now these elementary symmetric polynomials can also be written in terms of the matrix itself. So E0 is 1 by definition. E1 is just a trace of the matrix. E2 is a sum of trace of the square and square of the trace, so that combination. Then you have cube powers of the matrix and their traces, and that gives you the third elementary symmetric polynomial, and the fourth one is just the determinant of the matrix. So these are the elementary symmetric polynomials of any matrix S, a 4x4 matrix S. Okay, sorry, not matrix, but matrix. This is a general matrix. Okay, now they appear nicely whenever you want to look at the determinant of 1 plus S. So if you look at a matrix identity plus S and take a determinant of that, that determinant is just the sum of elementary symmetric polynomials of the matrix S. Okay, this is of course a very basic and simple result. Okay, so why are we emphasizing that here? For a very important reason. So look at this guy. Okay, look at this guy. This is determinant of 1 plus S, sum of elementary symmetric polynomials. Now, take a very similar sum, but put arbitrary coefficients in front of the elementary symmetric polynomials. Okay, and this is now, the claim is that this is your potential. So your potential has this form. It's just the sum of elementary symmetric polynomials of a matrix S with arbitrary coefficients. That's your polynomial. Then you say, oh, what's the matrix S? That is the crucial question. The matrix S is very interesting, and it came out of the work of the Ramgavadarse et al. And subsequent developments. So the matrix S basically is the following. You take the gravitational matrix G and take the inverse of this. So this is a matrix. Now you multiply this with the matrix F. So basically you are looking at, I don't know if the green is visible, so let me look at that. So you write G mu lambda F lambda nu. You look at this matrix. Okay, so one index up, one index down. So S is now the square root of this matrix. So G inverse F is a matrix by itself, is a 4x4 matrix, and S is a square root of that matrix. So the interaction is formulated in terms of the square root of a matrix. And the square root of a matrix is an interesting beast. It has very interesting properties, and it's much, much more complicated than the normal square root of a number. Okay, so that's the crucial point, that this theory, the interaction in this theory are formulated in terms of the square root of a matrix. And that matrix is the inverse of G times F. You can also look at F inverse G, it doesn't matter. You can equally well formulate it in terms of F inverse G. Okay, but you need one index up, one index down in order to be able to form polynomials out of this matrix. Okay, so to summarize, the claim is that the interaction term between the matrix, between the spin 2 fields F and G is given by the following quantity, that you take the inverse of the matrix G multiplied by the matrix F. Okay, and this is an object which has an index up and another index down. It's a 4x4 matrix by itself, but it's no longer symmetric. Now you take the square root of that matrix. And these square roots are very well defined mathematically. And then you define your theory with that. Okay, that's the claim. Okay, so this is the potential. So now we proceed. What is now the kinetic term for F? It turns out that the unique kinetic term for F, which renders the theory ghost-free, is again an Einstein-Hilbert term for F. So both spin 2 fields have Einstein-Hilbert terms as their kinetic terms, and then you have an interaction term between them, which is given in terms of the elementary symmetric polynomials of this square root of a matrix. Okay, and what are the parameters in this theory? You have a number of parameters. You have the Planck mass for the G matrix, the Planck mass for the F matrix, MF and MG, and then you have a number of parameters beta, which are in fact 5 in number. Beta 0 is a cosmological constant for G. Beta 4 is a cosmological constant for F, and beta 1, beta 2, and beta 3 are 3 other parameters in this theory, okay, which will of course affect your physics, but they are not known parameters. Okay, so this is the structure of the theory. Okay, and the claim is that this theory is ghost-free. So that we need to analyze. And of course, as you can imagine, this analysis becomes very complicated because of the fact that we have this, because of the fact that we have this square root of a matrix in our formulation. And handling this square root of the matrix is a bit tricky. Okay, so that's the source of the complication, basically. But we now basically know that this is almost a unique, unless you introduce derivative interaction between the fields, then this is the unique theory of interacting spin 2 fields, basically. Okay, so from this Lagrange,
what is the value of the mass parameter in this case for the field F?
You can actually you can calculate that. So there is a mass. You mean for the massive field?
Yeah, basically, I guess it will be some combination of MF and
it's a combination of MF, MG, and the beta parameters.
Okay.
So that depends on your solutions, and you can actually have a wide range for that, from small values to large values. Okay, but if you look at the phenomenology, then large values of the mass are preferred, basically.
For instance, if you want to impose that there is no tachyon, you will get some constraint on this.
Yes, exactly. Yes. Okay. Yeah. So you need to impose constraint that there is no tachyon. Yes, and but those are very wide ranges that are still allowed, basically, after imposing those conditions. Yeah.
Mm-hmm.
Yeah.
Okay.
Philip?
Yeah.
Yes.
I think what you want to do here is you want a coordinate transformation in the GRG sector to leave it alone, and in the FRF sector to leave it alone.
Well, I mean, so the general.
I mean, is this expression coordinate invariant?
Yes.
So
but this expression is coordinate invariant provided you transform both F and G as well-defined rank 2 tensors.
Yeah, that's what I'm asking.
Yeah,
yes.
yeah. So so there is one copy of general covariance. So this action has completely standard symmetries under a general covariant transformation.
Okay.
Okay. Yeah. So this is one. Thank you for pointing that out. Actually, this action now has complete general covariance, and F is dynamical. So first of all, now you see that it has a bimetric structure in the sense that both F and G appear like Einstein-Hilbert matrix, basically. So that's why the name bimetric. Now, going back to this work of Isham, Salam, and Strati, where they looked at a bimetric theory, they also had a theory like this. The interaction term that they had, of course, was not this one. That's why they had ghosts. But there, they introduced the Einstein-Hilbert terms, the same Einstein-Hilbert term for G and F, just by hand. But in this construction, we don't have a choice. This is the only option, basically. Okay? So the fact that we have a bimetric structure is completely dictated by the absence of ghosts. If you look at this theory, then at the propagating modes that I will very briefly describe, you get 7 propagating modes. So 2 of them correspond to a massless wave, 5 of them correspond to a massive wave, and there is no Boulevard-Dazer ghost at the end of the analysis. So so you get just the physical content that you want, nothing else. But the massless and massive modes are not just G and F, they're combinations of G and F. Okay, so the G and F mix, and then you have the mass and massless eigenstates, as I will describe later. Okay, and then as I said, there is no ghost. Okay, now how do you couple this to matter? Now it turns out that, again, the requirement that there is no ghost dictates the matter coupling. It tells you that the matrix G and F cannot couple to the same type of matter, first of all. They have to couple to different kinds of matter. And the different matter couplings are just minimal couplings. So the matrix G mu nu will couple to a copy of the standard model exactly as in general relativity. And the matrix F mu nu will couple to another copy of its own fields exactly as in general relativity. So these are both minimally coupled Lagrangians between the two fields and matter. And an implication of that also is that if you take G mu nu to be the gravitational matrix, that this G mu nu couples to the standard model that we see, then F mu nu cannot couple to the standard model. Okay, so the other spin 2 field can only interact with gravity and not with matter at all. Okay, which makes it a very good candidate for dark matter, basically. Okay? Except that you cannot detect it in particle physics experiments, you cannot detect it, at least not easily, because it mainly interacts gravitationally. Okay, which of course from the point of view of dark matter is quite reasonable, because dark matter, we have only seen dark matter in the gravitational sector. Okay, so this is about matter couplings. Okay, so
sorry,
yeah.
I have a question.
Yes.
Do we change equivalence principle with these theories?
Okay, not the weak equivalence principle. So the weak equivalence principle, which is about coupling gravity to matter, remains exactly the same. That's given from here. Okay, so the fact that matter moves in geodesics of a matrix remains exactly the same. The strong equivalence principle is changed because now the equation of motion for the matrix gets modified. It gets sourced by the other spin 2 field. So you change the strong equivalence principle, but not the weak equivalence principle. Okay. And the weak is the one which is more kind of better established. Sorry, Philip?
Yeah, I'm sorry to ask so many questions. Please. If the F sector does not minimally couple to normal matter, then how can it affect the motion of normal matters in a galaxy? I mean, how can it serve in any way for dark matter? So it has to normal matter to modify geodesics.
Exactly. So there are weak couplings. I may come to that later, but I will not spend. There are weak couplings via gravity, basically, via standard gravity. Okay, so the only effect is through standard gravity. Okay. Yeah. So there are some papers on this, basically. I've not checked the most recent things, but there are kind of calculations for this thing. But you are definitely right that it's not completely obvious. Okay, so now let me look at just a very brief sketch of this analysis of the ghost, basically. So the basic idea is that if you take the matrix G mu nu, and if n and ni are its lapse and shift functions, and you again write the lapse and shift of the matrix F, then the Hamiltonian for the theory takes this form, basically. So you have the Lagrange, the lapse and shifts as Lagrange multipliers. You can write them in different ways. This is one choice, basically. And then you can see that if you look at the equations of motion for these lapses and shifts now, you basically get 4 constraints here, 1 constraint here, and then you require that the constraint C1 equal to 0 is stable in time. Then you get a second constraint, and you combine this with general covariance, and then you see that you get the correct degrees of freedom, the correct count for degrees of freedom that you need, basically. Okay, so okay, now as you can see, in order to prove that there was no ghost in this theory, we have done a space-time, a 3+1 decomposition for the matrix G and F, and we have assumed that both matrix G and F have the same notion of space and time, and that is not given. So the question is this valid or not? Can one have simultaneous 3+1 decompositions for the matrix G and F? The answer is yes, and I will come to that later. That's a very, very important aspect of the theory, but a priori, you can ask that question. Okay, the answer is yes, and I will come back to that. Okay, so let's now move on. Maybe I skip this part.
Can I ask a question?
Yes.
No, so you're saying that the lapse and shift is the same for both of the metrics. But can you go back to the previous slide?
This one?
Where you were showing, this one. So here you're writing for the Hamiltonian, you're using L and Li and N.
Yeah.
But I mean, it's the same, right? I mean, so shouldn't you be able to write?
Very good. Exactly. Yes. So I can also write it in terms of N and I and L. So it turns out that at some stage you have a choice. You have to make a choice, but they are completely equivalent. Okay. So in the analysis,
mixing, I guess, or something.
Sorry.
This is where you get mixing of the two.
So this is a consequence of the fact that you have mixing, exactly, yes. But at some stage you need to solve your equations, and you have various options to solve the combination of 1 and 2, 2 and 3, etc. But all of them are equivalent, basically. Okay? So yeah. So just to do the calculations explicitly, you need to proceed in a certain way, but you can show that you will always get the same set of equations and constraints. Okay. Yeah.
No, I mean, my question was that if you're doing the simultaneous 3+1 decomposition and it's the same decomposition, then shouldn't the lapse and shifts be the same for both the metrics?
No. So the decomposition is not the same exactly, but the idea is that both matrices have the same time direction and they have common spatial hypersurfaces. So actually, I will come to that in a short while.
I see. Okay. Thank you.
I will come to that in detail, basically. Yeah. Okay. So I have something about what is called the Benson-Peldane or the Heumann-Kuchar-Teitelbaum matrix, which I will not describe here. But if there are questions at the end of the talk, I can come back to this and answer this. I think this is probably the only part of the talk which is related a bit to quantum gravity, but I will not talk about it now for the lack of time. But if there are questions, I can come back to it. Okay, so now we move on to the equations of motion. So this was our action. We write down the equations of motion. So the equations of motion look like this. So as you can see, this is the Einstein tensor for the geometric. This is the standard matter energy momentum tensor for the geometric. So the only difference with standard Einstein equation is this extra piece which involves G and F. And same for the F theory, the Einstein-Hilbert term for F, the energy momentum tensor for the F sector, and then another contribution which gives the interaction between F matrix and G matrix. So the structure of the equation of motion is rather simple in this way. And then in fact, these equations have a set of solutions where the two matrices are proportional to each other. And for these configurations, the solutions are exactly the same as solutions in general relativity. Okay, so this is an interesting set of solutions. These are interesting classes of solutions, from which you can obtain a lot of insight into the theory. Okay. So in particular, for example, if you take one of these proportional backgrounds, which are general relativity solutions, and you look at perturbations around those backgrounds, then you can see that the action can be diagonalized for the perturbations in terms of two modes, delta capital G and delta capital M. This one is massless, that one is massive. Okay, so this one has a fierce Pauli action, and this one has a linearized GR action, basically. And these are the combinations. Okay, so okay, now what are the limits of the theory? Suppose you take G mu nu to be your gravitational matrix, then the Planck mass of G mu nu basically becomes the physical Planck mass. Okay, and if the Planck mass of F mu nu is much smaller than the Planck mass of G mu nu, so G mu nu is the standard Planck mass, F mu nu could be, suppose, a TV scale Planck mass, then this limit is correct. And in this limit, the theory looks very much like general relativity. The opposite limit is where a theory looks like massive gravity. Okay, so I will not talk more about this. Okay, so now there's a lot of work done on the cosmology of these bimetric theories. I will not talk about that, but just to give you a feeling, you can basically fix the matrix G mu nu to be your gravitational matrix, and you can have a kind of FLRW answers for them. And then the equations of motion look like this. Okay, so that's the Hubble parameter. This is exactly like the equation for standard cosmology, where this contribution is a cosmological constant. Now, this is a model where we did not have a cosmological constant from the beginning by hand, but a cosmological constant emerges from the parameters of the theory and the mass, etc. Okay, that's a matter density. And then you get corrections. And as you can see, the corrections are small. They are small in h squared, and they're also small in the parameter alpha, where alpha is the ratio of the Planck masses, which goes to 0 in the general relativity limit of the theory. Okay, so you can see that if you want to look at cosmology, then this is the generic kind of behavior, and you have corrections that become more important as you go back in time. But late cosmology becomes very similar to GR for the correct ranges of parameters. Okay. Now let me skip this stuff. Okay. Now I come to something very interesting, which is relevant to the question that you asked. And I will try to do this in a few minutes. Yes, Philip?
Yeah, if I may be permitted another question.
Yeah.
I didn't follow completely, but it seems that your condition F bar equals C squared G bar enabled you to get this particular solution, but you didn't show that there were no other solutions that might still lead to ghosts.
No. So this
I mean, the theory is not necessarily ghost
point.
free. It's just that, is it just
No.
that particular solution?
Okay, no. So when I prove the absence of ghosts, I look at no solutions. I look at the theory and just look at the equations without, I don't need to look at solutions. I looked at this solution just to look at the mass eigenstates.
Good, thank you.
So around these solutions, one has nice mass eigenstates which do not mix. So this 7 degrees of freedom split into 5 plus 2, massless plus massive, and this split is nice around these kind of general relativity backgrounds. If you look at more general backgrounds which are kind of peculiar to bimetric theory, in which are not the same as general relativity solutions, then these 7 modes that you see, these helicities, their classification becomes more complicated, basically. Okay. You see 2 massless modes, but the 5 massive modes do not all appear as 5 massive modes. They split up. You see them as helicity 2, helicity 1, and helicity 0. So they have different behavior, different speeds, etc. Okay. So this was just a toy example to see the mass eigenstates properly. Yeah.
Okay,
but the ghost is not there around any background. Okay. Now, this theory, that the way that we wrote it down looks nice and all that, but if you look at it in more detail, it has problems that basically, in principle, could kill the theory. Okay. So how much time do I have actually?
Approximately 5 minutes, but
okay.
We started a bit
10 minutes.
later, I think.
Okay, up to 10 minutes. It would be okay.
So I take it to be 10 minutes. Thank you. Okay. So if you look at this theory, you have basically fundamental problems with this and different types of problems, okay, that could essentially kill the theory. But it turns out that these problems all have the same solution. So that actually becomes the strength point for the theory. Okay, so what is problem? Problem 1. Problem 1 is that you have 2 Lorentzian matrices, and each one of these matrices has a notion of space and time. And nobody told us that the times and space notions of the 2 matrices should be compatible with each other. So in principle, for example, if you want to plot the null cones of these 2 matrices, you can have all these configurations. Okay, this is a good configuration because the null cones intersect, so you have a common time direction here. Okay, and especially if they remain locked. This is a very bad configuration Okay, because in this configuration, you have no space-like surface, which is space for both of them. If you draw a space-like surface for the, like this, for the red matrix, for the blue matrix, this is not a, this is time-like. Okay, so this configuration has no common space-like surface for both matrices. Okay, and if they are not locked together like this, then the notion of space and time can change as the matrix can, as the tilting can change and evolve. Okay, so it's not clear if these two matrices have common notions of space and time. And if they don't, then of course a Hamiltonian formulation does not exist. Consistent time evolution cannot be carried out using equations of motion, etc. So then you will be sunk. So this is one major problem that you can have from the beginning. Okay.
Oh, excuse me,
Yeah.
I don't see, maybe you could explain, what is the difference between your picture C and picture D?
Yeah,
because
exactly.
both corner cross-section,
Yes.
but there are some something we
Yeah.
don't touch each other,
Yeah.
or what?
So C and D are the same. You are right.
Mm-hmm.
Yes. Yeah.
Okay.
So C and D are just written in the same, just to say, okay, there are these configurations, but they're equivalent, but they can still be tilted in different ways, but these are okay. Yeah. So C and D are, they're exactly the same. Thank you. Yes.
Okay, thank you.
Yeah. Okay. So the second problem is this. We wrote down the theory in terms of the square root of a matrix. But if you look at the square root of the matrix, there are many, many problems and issues with it. First of all, it's not unique. A matrix has many, many, many different square roots. Okay. Secondly, you write down this square root of a real matrix, but the square root itself could be complex or imaginary. It doesn't have to be real. Okay. And thirdly, the square root may not transform covariantly. Okay. So the square root is highly problematic. It's not unique. It's not necessarily real, and it's not even covariant. Not necessarily covariant. Okay, in the sense that it does not transform, even though it has one index up and one index down. It may not transform like a 1-1 tensor under general coordinate transformations. Okay, it may or may not. Okay, so this could be a big problem basically. And now, however, all these issues actually get resolved in the following way. Okay, that first of all, as we said, the square root is not unique. So first of all, you have a number of square roots which are called primary and some which are called non-primary. All the primary ones are good. Okay, the primary ones are good in the sense that for primary square roots, this quantity, the square root, actually transforms like a 1-1 tensor. So when you build functions from it, your action is generally covariant. Okay. For non-primary square roots, this quantity does not transform like a 1-1 tensor, so your action will not be covariant. So you will lose covariance. Okay. So you need this. I can explain this in more detail if there are questions later on. But so you need the square root to be primary. But then one can see that of the many primary square roots, all of them can generically go to non-primary ones. So as your configurations change in space and time, as you move around, you go forward or backward in time, a primary square root can always go to a non-primary square root, so you run into trouble, except for one specific primary square root, which is called a principal square root. And that principal square root is very similar to the principal square root of ordinary numbers. Okay. So there's a unique square root, which you call the principal square root, and that is the one for which your theory is generally covariant. Okay, so that fixes uniqueness and general covariance. So whenever you write the square root in the theory, you demand that by this, I mean the principal square root. Okay, once you fix that, then you fix the uniqueness problem and the covariance problem. Okay, but reality may still be a problem. Okay, so, okay. Sorry. Yeah, okay. So you demand that the square root is, whenever you write square root, you mean the principal square root, and that makes your theory unique, and it also restores general covariance. Now, your square root may be imaginary or real. Okay. Now you look at the possibilities and you find out that if you demand the square root to be real, then you only have to restrict yourself to situations where your null cones always intersect in this way. Okay, so requiring that the square root is real, you restrict yourself to this. Okay, so basically your theory is well defined only for real square roots, which also means intersecting null cones for the metric, which also means compatible space and time decompositions. Okay, and once you are in these configurations, then you can show that dynamically you cannot go out of them. Okay, when you start from this configuration, you remain within these configurations. There is a last possibility where the null cones are completely complementary. So suppose you have this null cone for one metric, okay, and the complementary one for the other metric. Okay, where so your notion of space and time are completely complementary. That's a possibility here. The square root here is real, but this is not principal square root. So your theory is not generally covariant for this choice. So this choice you have to throw away. Okay, and in fact, you can argue that this starting from these configurations, this bad configuration never arises dynamically. Okay, so this is so once you require that your square root is a principal square root, and your metric configurations should be such that your square root is real, then you just retain the correct ones for which you have compatible 3+1 decompositions, compatible notion of space and time. And in particular, you throw away this one. So why do I emphasize this one? This is because for several years, there were a number of papers that were written claiming that these bimetric theories were admitting closed time-like curves and a causality, etc. Okay, by looking at some cases. And it turned out that all of those cases where the calculations were correct, all of them actually pertain to this configuration, to this one, okay, which now we have excluded from the theory, basically. Okay, so that was an interesting feature. Okay, so just to summarize this point, we basically started from the statement that our action could be highly problematic because we had a square root, which was not necessarily unique, which could violate general covariance, which in principle was not even real. And we had a problem with the two Lorentzian matrices for which the notion of space and time did not necessarily correspond to each other. But then we saw that once you demand that your theory is well formulated, then you need to restrict yourself to the principal square root. And you also have to look at configurations where the square root is real. Okay, and that essentially solves all the problems. Okay, so the action became completely well-defined. And it was interesting, of course, because when the action was formulated, these properties were not known. But it turns out that these are actually all built in the formulation of the theory. Okay, okay, so that's it. Okay, then I wanted to go to multiple spin 2 theories. And for that, of course, I don't have time. So I will just spend maybe 1 minute on that, which is that if you want to now go beyond 2 spin 2 fields, it turns out that you need to write down the theory in terms of Vielbeins. There is no metric formulation. And even in terms of Vielbeins, the theories that were proposed a few years ago, it turned out that they generically had ghosts, even though at the first look, they seemed to be ghost-free, but they were actually ghosts. So then it was not clear if theories with more than 2 spin 2 fields, which are ghost-free, exist or not. Okay, so however, now we know that there is at least one such theory which is ghost-free, and that has this very simple structure. So you start with n Vielbeins, so E1, E2, E3 up to En. Take a linear sum of all these n Vielbeins and take a determinant of that. That is your interaction term. And then for the kinetic terms, you just add n copies of the Einstein-Hilbert action. Okay, so the claim is that this theory is ghost-free and well-defined. And so this is yes.
Excuse me, I have just a trivial questions.
Yes.
What means beta in the power 1, or this is the index of beta? Just one parameter beta.
Yeah, this is just counting beta. Yeah, these are different. So beta 1 is one parameter.
Different powers. Okay, thank you.
Exactly.
Thank you.
So yeah,
Thank you very much.
actually I don't remember why I wrote it up and down. In principle, I could have written it all down.
Because it's look like up and down indices.
You are right. So I have to change that. You are definitely right. Yes, yeah. These are just n parameters. Yes. So this is the theory. Okay. So, and the details of this will hopefully appear in March, in a paper in March with Joachim Flinkman. And so for this theory, we have again looked at various at the proof of the ghost at a more detailed level, and also the solutions, some of the solutions, and also the mass spectrum. And again, it turns out that the mass spectrum is very nice in the sense that when you just write down the mass spectrum, you could have lots of tachyonic modes and all that. But under very general conditions, the masses are all stable and etc. So I will not go through the details of this. So, but hope this will come out in a short while, basically, with Joachim. Okay, so that's the end of my talk. So then just very briefly to kind of go through the discussion and results, to go through discussion. So this is basically the beginning of our understanding of spin 2 fields beyond general relativity. We know the bimetric case, the multimetric case, we don't know. We don't know what are the conditions on derivative interactions, which we have not even investigated here. That has been investigated briefly by other people, but so those are the things basically. Okay, and then within this set of theories, so the notion of causality, there were lots of claims that these theories are not causal, but from the various cases that we have seen, these are actually causal. There is no problem with causality, but the mathematical proof is kind of lacking still. Superluminarity, yes, around non-Einstein and not flat backgrounds, you have superluminarity, but in the sense of faster than light travel. However, these are not Lorentz invariant backgrounds, so the theory is not necessarily acausal. There's a finite speed in the theory, so this is okay, this is not problematic. A feature of this theory is the unavoidable mixing of mass eigenstates. In the standard model, we know that quarks and in particular neutrino masses mix, but that's a feature that we need to put in by hand because the nature requires that. But it's not something that comes from the theory itself. In these multiple spin 2 theories, to my knowledge, this is the only situation where mass mixings are completely dictated by the consistency or absence of ghost in the theory. Okay, so you get when you get mixing between mass and when the mass eigenstates and interaction eigenstates are not the same, that mixing is given entirely by the theory itself. Okay, as a result of the absence of ghosts, and you don't need to put this mixing by hand. So this is in contrast with the standard model, where in principle you can write theories of fermions which are not mixed, but nature tells you that there should be mixing. So it's interesting to see that, okay, if there's a connection between the gravity sector and the matter sector, if the mixings of the fermions could have some kind of origin in these mixing of spin 2 fields, but this is just wide speculation. I have no reason to believe in that, basically. Okay, and then of course, okay, we have, as I mentioned, the systematics of multiple spin 2 interactions beyond bimetric theory. So when you go to more than 2 spin 2 fields, we know by now certain examples, but we don't know the full formalism to write down the most general theory of multiple spin 2 fields. So the question is if we can find that out. And of course, the last thing is to have modified kinetic terms. We have modified to have derivative interactions between various spin 2 fields. And this is interesting because if we want to have these theories with extra symmetries, then we want such kind of modified kinetic terms. And these arise naturally, for example, in this kind of McDowell-Mansouri type of constructions of general relativity that can be extended to higher groups. And those constructions naturally give rise to multimetric, bimetric or multimetric theories with modified kinetic interactions. Okay, so that's the end of my talk. And Thank you.
Oh, okay, thank you very much for your interesting talk. Question, please. Okay, Philip, please start our discussion. Yes.
Yes, first of all, thank you for this nice presentation.
Welcome.
I have a question which is so totally simple.
Okay.
You just take the flat metric, it's diagonal, its elements are -1, 1, 1, 1.
Yes.
Its square root is not real.
Yes.
So two questions. One is that the reason why there's a ghost? And the other question is, why is it that you are able to exclude the flat metric if you require that the square root be real?
Yeah. So that's a very good question. So the thing is that here the square root is always of G inverse F.
Okay.
So if I take the matrix G to be -1, 1, 1, 1, and I take the matrix F to be
Also
1,
has to be
-1, 1, 1, like that.
Yes.
Then of
Okay,
course
so
I have
G to
-1,
-1 F
-1,
is
1,
real.
1.
Yeah.
And this also is a situation where the space and time of the two matrices are not aligned. So
Yes.
this is a configuration that I don't want. And obviously, as you pointed out, if you look at the square root of this matrix, it's not real.
It's not real. Yes. Very
So
good.
if I require that my square roots have to be real, then the theory must restrict itself to configurations where this is not allowed.
Ah.
Okay, so that's a very good point. It's a very good example of this. Okay, so by
Okay.
demanding real square root, you are essentially excluding these configurations. That's one. Okay, but another thing that in connection with what you said, suppose that I take my G and F to have the same space and time directions. So suppose this is now 1, 1, 1, 1.
Yeah.
Okay, this is now perfectly fine. They are completely aligned with each other. Okay, let's take the two-dimensional case. So that this is 1, 1, like that. Okay, so both matrices are identical. There's no problem with that. But if I take the square root of this matrix, I have two possibilities. I have a possibility which is like this is 1 square root.
You have 4 possibilities.
Okay, yeah. So I identify the overall signs. Okay, so plus, minus, I identify both of them. This is not, for me, these are equivalent. But the other possibility is 1, 0, 0, -1, up to an overall sign. Okay, now okay, this is what we call a primary square root. This is a non-primary one. And if you actually look at this combination now, you can see that this one respects general covariance. This one does not respect general covariance. Okay. So what I mean by respecting general covariance, suppose you have a matrix A and you take the square root of that. Okay. So which is, it will be something. Okay. Now suppose I transform, so if this matrix A has one index up and one index down, under a general coordinate transformation, it will transform to something like this: Q inverse AQ, where Q is like dx by dx tilde kind of a matrix of coordinate transformations. Okay, so this is A in different frames. Now, if I take the square root of A tilde, then for a good square root, this also transforms exactly like this. So if A is a matrix, then if A is a good tensor, then its square root also is a good tensor. Okay, so if my square root transforms in this way, if A transforms in this way, then I'm happy. But this happens only for primary roots. It happens only for this kind of root. If I take this kind of root, you can easily check that this is not true. So that cuts down the possibility of square roots. So if you have many square roots, there's only one which is good, and that's the one for which this property is satisfied all the time, basically. So sorry, this may be a bit confusing, but it was in relation to your question in some way, but yeah, anyway. Okay, so yes, Filippo?
Yes, hi, can you hear me?
Yes.
Yes, thank you very much for the nice talk. I was wondering about the meaning of the beta coefficients.
Yes.
Like, are they coupling constants between the spin-2 fields?
Yeah.
Okay, and so in the case of flat reference metric, so the massive gravity, what's the role like? Are related to the mass of the graviton or
yes, exactly. So in the case of massive gravity, they relate to the mass of the graviton. They also give rise, the theory also has a cosmological constant. Okay, of course, if you take a flat F mu, then you need to make sure that the cosmological constant cancels out. So you need to tune these beta parameters in such a way that the resulting cosmological constant becomes 0. Otherwise, the beta parameters will give you a cosmological constant. Okay. And then, of course, they will tell you about deviations from GR, because the mass parameter is just one combination of them. Cosmological constant is another combination of them, but then you have more than 2 of them. So then the other ones will just tell you how your theory starts deviating from GR.
Okay, and I think I read that overall we are left with 2 free parameters in the case of massive gravity, right?
So that is if you fix in the case of massive gravity, and if you fix your space to your background space to be flat.
Okay.
Yes. Yeah.
Thank you very much.
Welcome. Deepak?
Okay, I see a next question from Deepak White. Deepak, please ask your question.
Yeah, hi. Fawad, thank you for this talk. Recently, I became very interested in biometric gravity in the context of string theory, actually. So I was wondering if, because if you, for instance, if you look at the action of a string, you have the Nambu-Goto term, right? I mean, I assume you are familiar with like the minimal basics, if I can ask a question about that.
Yeah, my PhD was in string theory.
Oh, I'm so sorry. I'm so sorry. I'm so sorry.
Very long ago, but still.
Okay. So you know the Nambu-Goto action. So yes. I mean, I guess the question is very simply this: that what if you write down an action with 2 metrics exactly the same way? A Nambu-Goto term for each metric, and then you could have a interaction term also. So I looked in the literature, and people have looked at the the possible relationship between string and biometric gravity, but not a biometric string itself.
Yeah, exactly. So you are definitely right. So what people have looked at basically is the fact that in string theory you have a massless spin-2 field, and then you also have a massive spin-2 field. And people have tried to regard that combination of massless and massive as a kind of biometric theory. That generically does not work because the mass scale of the massive field is of the same order as the scale of derivatives in the theory. So generically, if you write that theory, you cannot exclude the extra derivative interactions, basically. At least that's my understanding, unless you tune things finely in some way. So that does not seem to work. Now, your question, that's a very interesting thing. So I have actually thought about that more in the context of the Polyakov action kind of thing, if one could generalize that to a biometric setup. So I'm kind of convinced that standard string theory will never give you biometric, because you essentially start from a single Minkowski metric, and you basically build the theory with essentially with a kind of minimal coupling in the back of your mind, basically. So it can only give you GR and nothing beyond that. So that's kind of built into string theory. And that's why also you get only one type of closed strings. Now, beyond that, yes, you're right, but I myself, I have not figured out a nice way of writing interactions between the two matrix. There are Yeah, I mean, if you use field binds, you can actually write down a worldsheet action, which is a combination which contains both field bind, two types of field binds. Okay, you can do that. But I have not been able to actually develop that further into a consistent structure. So that's a very interesting question, but the answer is I don't know.
Well, I've recently done some work in that direction. It's working
Oh, very
unpublished.
nice. Okay.
So, I mean, maybe I can contact you if you're
That I
interested.
would be very interested in that. Exactly. Yes. Yeah.
Okay. I'll drop you a mail.
Okay.
Yeah.
Okay. I see the question from Shravan.
Yeah.
Shravan, please ask your question.
Hi, Fawad. Thanks for the very interesting talk. I have a question related to dark matter. So,
Okay.
well, the idea of dark matter is to make the Einstein theory intact. So you put all the matter which is invisible, not interacting with standard model. I got confused when you explained that the bimetric theory is useful for dark matter, and especially your matter which is outside the standard model can couple to the new metric. So you kind of merging, you're modifying Einstein theory and adding dark matter. Well, it would be nice if you do not add any matter. Some modification of gravity already explains all the enigma related to dark matter. That would be the perfect, but I'm just trying to understand what.
Good. So the people who have looked at this as a dark matter candidate, they don't actually introduce dark matter. So the extra matter that coupled to the second matrix, that is not introduced.
Okay.
Okay. So all you have is the standard model coupled to gravity G mu nu, and then just one F mu nu which couples to gravity.
Okay.
Okay. But then what happens is that the massless and massive modes are linear combinations of F mu nu and G mu nu. So as a result, even though the G mu nu matrix couples to standard model matter, but this G mu nu is a combination of massive and massless. So when you look at the fluctuation of this delta G mu nu, this will be some massless mode that I write as capital delta G mu nu plus a small parameter times a massive mode.
Okay.
So there is a kind of coupling between massive spin 2 particles and the standard model. It comes via the diagonalization of the perturbations, and it's always suppressed by a very small parameter here, basically.
Okay.
So,
but this massive mode, will it act as a dark matter?
So the claim is that this massive spin 2 particle, these guys actually act as dark matter. That is the claim. So that if you search, there are maybe I can find out and send some references for you. So I think there are at least 2 groups who were actually looking at this problem. I have not followed things in detail, but their claim was that this is a consistent dark matter model, basically.
Well, I mean, it's actually a modification of gravity, so in some sense, right? Because
so it's exactly, it's a modification where your dark matter is not coming from the standard model sector. Exactly, it's a modification of gravity. Yes, yeah.
It's actually a hybrid, I think. Normally, you write Einstein tensor equals energy momentum tensor. Problems change the energy momentum tensor by introducing new matter particles. That's the standard picture.
Yes.
Alternatively, you can say, I can alter the G mu nu side. That's modified gravity.
Yeah.
What you're doing is a sort of hybrid. You're saying, I'm going to modify T mu nu geometrically. Rather than modify T mu nu as new particles.
Yeah. So
that's why I'm calling it a hybrid.
Yeah, that's, I think maybe, yeah, probably. Yeah, of course, the T mu nu of matter, we are not modifying. So
exactly.
Matter is a standard model matter. But yeah, maybe one can look at it from that, in that sense also. Yes. Yeah. Yes.
Okay. Well, I'm very, very curious to look at the references you mentioned. So Yeah, it is interesting to understand. Well, my
Yeah.
second question is actually kind of related to that. Basically, understanding early universe CMB requires lambda CDM. So I don't know if any studies have been done with biometric theories which fit lambda CDM. I mean, there are initial conditions due to inflation that is separating that part. So lambda CDM is the essential element for
Yeah.
CMB multipole
Yeah.
curve.
So there are studies where basically you look from BBN onwards. And from BBN onwards, you can actually match the standard cosmology.
Mhm.
Okay. Now, for the actual inflation, so far, what people have done in the back of their mind, they basically assume that, okay, yes, there is inflation, there is the standard mechanism of inflation, etc. Okay, that one has not been worked out. Okay, but that's the general thing. For me, that's not very interesting.
Yeah, my question is about CDM. Early universe, you need CDM component, and how the biometric theory can give the CDM required for the to fit the any observations of the early universe.
Yeah. So I think one thing, the lambda here can actually come from the theory.
Okay.
Okay. So one thing is that, so the lambda, so in principle, you can start from the standard lambda that we put in the action, that can be 0. Okay. Then the parameters of the interaction, they can actually generate a small lambda.
Okay.
Okay. And the small lambda generated by the interaction, the argument is that that is actually stable under quantum corrections. Okay. So then of course you can say, okay, but how did you throw away the original lambda? That's a different question. So the lambda can come from this theory. The dark matter part, of course, there are these, as I mentioned, there are these papers that claim that dark matter can emerge from this theory, but I don't know how detailed the analysis has been done there, like in the sense that if people have looked at like the complete evolution of the theory from like early inflationary part onwards, from end of inflation from BBN onwards, with the dark matter coming from the theory. So I don't know how exhaustive those analyses are, but in principle that's possible. But if you want to go to early times and like say, okay, inflation, then the way that people have been thinking about this problem, you don't say anything about inflation. Okay? From BBN onwards, I think that you can describe reasonably consistently in the theory.
Okay.
Okay, with the lambda coming out from the theory itself, and hopefully the dark matter also coming out from the theory. Before that, I don't know. But of course, I would be interested in scenarios where you have, I don't know, some kind of alternative to Big Bang coming out of this theory itself, or something related to structure formation, seeds, or something like that. I don't know much about it, but I think that's the more interesting thing, basically. Yeah.
Okay.
Okay.
I also have a couple of questions.
Yes.
Okay, please ask.
So first of all, thank you very much for the talk, Fawad. It was very instructive. So I have a question regarding the biometric part, just with one massless graviton and one massive F mu nu. Let's call it massive graviton.
Yeah.
Is the massless limit for this massive graviton consistent in this biometric theory?
Where both of them become massless?
Yeah. I'm asking this because usually, as far as I know, there are like no-go theorem, which tell us that basically if you have a local Lagrangians, there is no way in which we can consistently couple two massless gravitons. The only way to do that usually is to admit that one of them is a ghost.
Yeah.
In that case, you can couple two massless graviton and one is ghost-like. So in your case, you start with let's call it healthy massless graviton and a healthy massive graviton. So I was thinking that maybe if you take massless limit, you may get some ghost again. I don't know. But
so in the standard setup, if you write a generic mass term and take that limit in a generic way, then the F sector of the theory becomes infinitely strongly coupled, basically.
Okay.
Okay. So that's one. That's one thing that can happen. The other thing is that suppose you compute the Fierce-Pauli mass. Okay.
Mm-hmm.
So you compute the Fierce-Pauli mass for this theory. This will be a function of the beta parameters.
Mm-hmm.
Okay. And also the Planck masses, say mg and mf, the two Planck masses. Now you can set this equal to 0 by brute force. It will just fix one of the parameters because you have like a few parameters in this expression. You can solve it easily and fix one of the parameters. Okay, so then you say, oh, now I have two massless particles in my theory. But then the thing is that this is a theory which looks like two massless spin 2 particles only at the linearized limit. But when you introduce interactions, then these conditions get violated. So in the presence of interactions, then you generate more, then the extra degrees of freedom come in.
Mm-hmm.
Okay, so then you end up with a theory where you end up with a theory where the number of your degrees of freedom change. At the linearized level, you have like 2 + 2 degrees of freedom. And when you go away from that, you have 2 + 5 degrees of freedom.
Mm-hmm.
So that usually is a sign of strong coupling, basically.
I see.
Yeah.
Sure. Okay. So
so I think the general answer is that no, you cannot actually reproduce two massless spin 2 fields from this theory in any consistent way.
Mm-hmm. I see. Okay. I see.
And more questions, please?
Just one last.
Want to add more? Okay, please.
Yeah, maybe it's slightly related. So in this sense, I mean, maybe the answer is no, but is there any way to have a Higgs mechanism for a massive spin 2 in this case?
Okay, so that's $1 million question.
Okay.
Nobody will give you that $1 million in reality, but for me, that is like the $1 million question. Yes, what is the Higgs mechanism? We don't know that. Okay. Yeah, so in fact, if you look at my older talks, this discussion also lists a Higgs mechanism for the massive spin 2 field as one of the things that we want to get, basically. Yeah.
Okay.
Yeah, there is a kind of, I think in 2009 or so, around 2009, there was a paper by Toft where I think it's called Higgs mechanism for massive gravity or something like that. But that was just a set of scalar fields that were introduced. And then when you look at the scalar fields around a kind of certain background, then you get, then they generate a mass term. But then one of the scalars actually is ghost-like, basically. So it's not a genuine, it's more like some Stuckelberg kind of thing. It's not a genuine Higgs mechanism. Yeah. But that question is very interesting if one can find, considering that for spin 1, you can generate masses via Higgs mechanism. Can you do it for spin 2 also? I don't know. Yeah.
Okay, thank you.
Welcome.
Okay, more questions, please? If there is no more questions from the audience, maybe I will ask some general questions.
Please.
You spoke mainly on bosonic sector. What about fermion sector? For example, what about spin 3.5? Can you introduce some analog of supergravity or something like this? Okay, this is important from the string field point of view, at least. Okay.
Yeah. So So there are some papers on supersymmetrizing of this theory. Okay. Yes. So now there are two kind of approaches that you can take towards supersymmetrization here. One is that you say, okay, I have a massless spin 2 multiplet. Now, what is my massive spin 2 multiplet? Let me construct a massive spin 2 multiplet and then put them together. Okay. So that's one approach. That approach has a shortcoming that the split between massless and massive eigenstates is visible in this theory only around certain backgrounds. So you write down the theory around the background, look at the linearized theory, and then you see, okay, I have a massless field and a massive field, which are combinations of the perturbations of the two matrix. So then you have, okay, your massive and massless multiplets, but then you know that if you go to the nonlinear theory, all these multiplets gets mixed in a very horrible way. And we have no control over what this means, basically. Okay? This is one thing. The other approach then is, of course, to formulate the theory in superspace from the beginning. Okay, so that approach, I know that there are some papers, at least one paper on this. But in that approach, the difficulty is that you write down the theory on superspace, but then what are the constraints that you impose on it? What are your superspace, the analog of superspace constraints? So like from my point of view, even in GR, if you look at those constraints, they look quite arbitrary, basically. You kind of impose a constraint knowing that, okay, this works, basically. So in this case, the analog of that is not obvious. At least to me, it's not obvious. So yes, you can write the theory in superspace easily. That's not a problem. But then what the constraint that you impose on that, the what you call the torsion constraints, basically. I don't know how to get that.
Okay.
Yeah.
Thank you.
May I ask a question?
Yes.
Okay, please.
Yeah. We know that Einstein gravity has finite one-loopers matrix. What's known about this theory at the quantum level? Sorry. You can, in principle, compute this matrix for this graviton.
Could you repeat the question? Sorry,
the question is about scattering amplitudes at one loop in this theory. So in Einstein theory, Toft and Weltman have shown that one loop gravitonous matrix is finite. So what happens here? Was that studied?
Yeah. So as far as I know, I am not aware of it. So in general, however, the quantization of this theory is a bit, so this is a theory with constraints. So of course, one needs to quantize not just in the standard trivial way, but you need to take the constraints into account, basically. So I don't know if anybody has quantized this theory in a really in a kind of in a trustworthy way.
Which constraints well, suppose we just expand near flat space or any background, like what you discussed, the G equal F, then you get massive and massless interactions and, well, propagator and plus interaction. So constraints
around flat space, of course. So the constraint basically is a constraint that removes the ghost.
Okay.
So you can expand that around flat space. I think this is the constraint that around flat space, this is like the linear curvature scalar vanishing or something like that, which is of course known from like massive gravity for a long time.
Okay, thank you.
But that's only at the linearized level. But I think the honest answer to your question is that I don't know.
Okay, thank you.
Yes, welcome.
Okay, more questions, please. Maybe I will ask the last question. My question is about row dimensional case.
Yes.
Does somebody try to study like a Jacques-Tetelboy model or the three-dimensional case? It would be interesting to hear your comments about it, please.
So this theory is completely dimension agnostic. So I talked about 4 dimensions, but you can do this in d dimensions and nothing changes. So the entire analysis is, so the number of terms in the interaction Lagrangian will increase because in d dimension, instead of working with 4 by 4 matrices, you work with d by d matrices. So the number.
If I work with 3 by 3 matrices, it will become easy or not? 2 by 2 matrices, what is the situation?
Yeah, so with 3 by 3 matrices, it will become easy because the potential will have less terms. So when I write the potential V, it was like beta 1 E1 plus beta 2 E2 plus beta 3 E3. Now these E's are the elementary symmetric polynomials of my square root matrix. G inverse F, square root, I call it S, and my E's are function, the elementary symmetric polynomials of this S. Okay, now, and then you have beta 4 E4. So in 3 dimensions, this will be 0. So you have less number of terms, and E3 is just a determinant. In 2 dimensions, this also will be 0. So you just have these 2 terms. So yes, in lower dimensions, your potential looks simpler. In higher dimension, the potential looks more complicated with more higher powers of the interactions. But the analysis of the basic analysis that the theory remains ghost-free, that is completely dimension independent. So in 3 dimensions, this theory has been studied a lot by the group of Eric Bergshoff and collaborators.
Oh, I see.
So they have, so they call it Zwei-Dreibein theory. So Zwei being 2, and instead of the matrix, they write it in terms of Vielbeins, which become Dreibeins in 2 dimensions. So that's called the, so the Zwei-Dreibein theory that they consider is exactly the bimetric theory in 3 dimensions.
I see.
Yeah.
Thank you.
Welcome.
Okay. More questions? Okay, we ask a lot of questions. You maybe people are tight. Thank you once again for your very interesting talk. And please don't forget to send us your transparencies. And also maybe people, we would like to know if you are not against to put your talk on YouTube.
You already asked.
Okay?
It's fine.
Yeah, that's fine. That's fine.
You already asked. Okay,
Yeah.
sorry.
Yeah.
So I missed this. Okay, thank you very much.
No problem.
Yes.
Yeah.
Okay.
Thank you very much.
Thank you.
Thank you very much. Thank you.
Thank you.
Bye-bye.